In this video, we're going to look at PV diagrams, pressure volume diagrams. So these are a plot of the pressure versus the volume of some substance. And the most important thing that we are going to get out of PV diagrams is that they are going to allow us to visualize the relationship between pressure and volume and allow us to calculate the work done through some process, particularly expansion or contraction of a gas. So let's imagine that I expand a gas at constant pressure. So I start out here on my PV diagram. I have some initial volume and some initial pressure, right? This could be, for example, a gas in a box, right? There is some pressure of this gas and it has some volume. And now what I'm going to do is I'm going to allow the box to expand, and I'm going to keep the pressure constant as I do this. And so, for example, now I might have a box that is this big. The same gas, right, it is now just spread out over a much larger volume. Okay. And I'm going to do this initially just at constant pressure. So my volume is changing here as the box expands, but my pressure isn't. So my PV diagram just looks like a straight line. Now, we know that the work done on the gas is equal to the negative integral of P dV. This is work done on the gas. Okay, well, this area here that I'm highlighting, that is the value of this integral, right? Work equals integral of P dV. That is the area under this line. Okay. First, where does this minus sign come from? Well, in the case of constant pressure, this work is simply negative P times V final minus V initial. And if V final is bigger than V initial, then this work done on the gas is negative, which makes sense because the gas is expanding outward while the force on the gas is inward. So the work on the gas you would expect to be negative, and that's where this minus sign comes from. If the gas expands, V final is greater than V initial, we expect negative work done on the gas because the force on the gas is inward while the expansion is outward in the opposite direction. Okay. So you can quickly just get a sense of what the work looks like by looking at the area under this graph. Now let's look at a specific example of a process, a cyclic process, a process that goes in a repeating cycle, and try to figure out the work done in this process. Okay, so the process will start at point A. We go from A, we expand at constant pressure to point B, where B has a V final is 3 times V initial. So we are tripling our volume at constant pressure here. Now, we can calculate the work done in this process as the area underneath the line. So from A to B, this area here represents the work, and we can find that by taking this integral. We integrate from V initial to V final, which is 3 times our initial volume, and we end up at 2P1 times V initial, and that work is negative because we are expanding the gas. That means we're doing negative work on the gas. Okay. Then we can go from B to C. From B to C, our volume doesn't change. So dV is 0, right? There's no change in volume between B and C. which means there's no work done on the gas. Okay, next we go from C to D. From C to D, we do exactly the same integral, except that our pressure has changed. So instead of from A to B, we were at some pressure P1, now we're at some other pressure P2. We go from 3V initial to back to V initial. And notice that because our final volume is smaller than our initial volume, we pick up an extra minus sign. So we end up doing positive work on the gas. So we compress the gas, that does positive work. And the work that is done here is actually the red marked area, right? Because it's all of the area underneath this line, and it's positive because we are compressing the gas. Okay, and then from D to A, we have no work done again, because again, there is no change in volume. If we look at our total work, we see that our total work is just the sum of the work in each component of the cycle. And the two of them are 0, and the other two are 2PV initial and 2P1V initial. Sorry, 2P2V initial minus 2P1V initial. That is the red area minus the purple area. And when you take that into account, what you end up with is just the area inside of the box, right? So just the black marked area. This area down here gets subtracted out when we do the total work around the entire cycle. Another thing that we can think about with PV diagrams is the total change in energy around a full cycle. Now, the energy of a gas, if you remember from, say, the equipartition theorem, U equals F over 2 NKT, right? So the energy of a gas depends only on that gas's temperature and the number of particles and the number of degrees of freedom, right? But the only one of those that's going to change as I compress or expand the gas is going to be the temperature, right? But I also know that NKT equals PV. Therefore, if I'm at a unique location in my PV diagram, say at point B, I'm at a specific pressure and a specific volume, and therefore I must be at a specific temperature, because temperature is uniquely dependent on pressure times volume. So if I'm at point B, every time in the cycle I get to point B, I must be at the same temperature because I'm at the same pressure and volume, right? And if I'm at the same temperature, then I'm at the same energy. And this tells us that the change in energy as I move around a full cycle, however I do it, if I get back to the same spot that I started with, my total change in energy must be 0. And because the total change in energy is equal to the work done on the gas plus the heat added to the gas, right? Heat Q, work W, we find that the heat added to the gas is equal to the negative of the work done on the gas, right? So the total heat added to the gas is equal to the negative of the work done on the gas. This is simply a statement of energy conservation. Right? Every time we get to B, we must be at the same energy, which means that energy inflow and energy outflow must be the same, must be equal to one another around the full loop, okay? And depending on what kind of a loop I make, I may be doing more or less work, and I may be absorbing more or less heat. But if I'm going to do more work on the gas, then the gas had better give up more heat so that the total change in energy stays at 0 when I get back to point B. Now, this does not mean that everywhere on the cycle, the energy of the gas is the same. It is just that every time I get back to point B, I better be at the same PV, the same T, and therefore the same U, right? When I get back to point B. Point C is clearly a more energetic spot on the PV diagram than point B. The pressure is higher, so PV is higher, which means the temperature is higher. So the U, right, the energy at point C is clearly larger than the energy at point B. And that's fine. In raising the pressure of the gas, well, I didn't do any work on it, so I had to add a bunch of heat into the gas to raise this pressure, right? Because there's no work done, but I raised the pressure and I increased the energy because I increased PV, so I must have added heat into the gas. So this line is adding heat into the gas. Likewise, this line from D to A, again, I did no work, but I dropped the energy of the gas because I dropped the pressure while not changing the volume. So I lost heat from D to A, I gained heat in the gas from B to C. Now let's look at a specific example of a cyclic process involving an ideal gas. So the setup is that we have a diatomic ideal gas that is initially at a pressure of 150 kilopascals and a volume of 6 cubic meters. The gas contains 300 moles of atoms, and the gas moves through the following cycle. First, there is adiabatic compression to half of the initial volume. So we're compressing the gas until it is half of its initial volume. We are then dropping the pressure of the gas. So the pressure of the gas is dropped at a constant volume until the gas reaches a pressure of its initial pressure, 150 kilopascals. And then we have isobaric expansion until the gas is at its original volume. So our goal is going to be to find the work done on the gas and the amount of heat flowing into the gas throughout each step of the process and for the process as a whole. Now, the first thing that I do when I look at a problem like this is I try to pick out any keywords or any key values that are given to me. So the keywords diatomic. This tells me that the number of degrees of freedom is 5. There are 3 degrees of freedom for translational energy and then 2 degrees of freedom for rotational energy. So my degrees of freedom is 5. I'm told the number of particles. I'm told the initial pressure. And I'm told the initial volume. Okay, so those are all going to come in handy as I try to do this. And the next thing that I'm going to do is I'm just going to draw a rough sketch. This isn't going to be super accurate, but I'm going to draw a rough sketch of what the PV diagram for this process is going to look like. So I'm going to start at some point here. I know that my first step is going to be compression, so I draw my first dot kind of out here so I know that I can compress from there. So I'll call this just V initial and P initial, where I know the values of these from the initial problem set. Okay, I have adiabatic compression. Adiabatic compression, for an adiabat, P is proportional to 1 over V to the gamma, where gamma is a function of the number of degrees of freedom. In this case, this is going to be 7/5. So the pressure is going to be proportional to 1 over V to the 7/5. So I'm going to get some kind of a steep kind of growth function out of this velocity, or out of this pressure. As the volume shrinks, the pressure is going to rise exponentially, to be exponentially large as the volume gets ever closer to 0. So I'll draw this a little bit better. Like that maybe. So this is my first step, my adiabatic compression. Okay, so I'll label that as 1. My next step is going to be that I arrive at half of the initial volume. So put that, say, here. And then I drop the pressure until I have reached my initial pressure. So this is just a straight down line here. And then lastly, I expand the gas back to its original volume. So I have a line straight back here. And I know that this isobaric means that the pressure doesn't change. So I'm expanding it back to its initial volume at a constant pressure. So those are my three stages. I have stage 1, adiabatic expansion. Stage 2, constant volume or isochoric compression or dropping pressure. It's not really compressing, it's just we're dropping the pressure. And then for part 3, we are expanding the volume back to its original state. So what we're going to do is we're going to try to analyze each of these steps individually and find the work that is done during that step and find out how much heat is transferred during each of these steps. First, let's consider the adiabatic process. The adiabatic process involves compressing our gas from some initial volume to some final volume. Adiabatically means that there is no heat transfer, so that all of the change in energy of the gas is due to the work done on the gas. Okay, to calculate that work, we're going to again use our adiabatic relation here between pressure and volume. And we simply do the integral as we have done in other videos previously of taking the integral of our work and finding this total work done, which is 719 kilojoules. So we have done a positive amount of work on our gas, and our gas has gained that amount of energy. So as we move from our initial point to our final point, we have gained energy based on the amount of work done. Next, what we want to look at is how much the energy of the gas changes as we complete the second step of our cycle, where the pressure of the gas is decreased while keeping the volume the same. In this case, we know that the change in energy is due only to heat flow, since the work done on the gas must be zero if its volume doesn't change. We're only considering compression work. Of course, there could be like electrical work done or some other type of chemical work done on the gas, but we're not considering any of those at this point. The only work we're worried about is compression work, and that must be zero if the volume doesn't change. Okay, so all of our energy change is in terms of heat flow. So what we're going to try to do is just figure out how much did our energy change in this process. And to do that, we're going to use the equipartition theorem, which relates the energy of the gas to the temperature, and therefore the change in energy of the gas to the change in temperature, because nothing else in this equation depends or is a variable that can really change with this gas. N is just the number of particles. We're not changing that, and we're not changing the number of degrees of freedom in our gas. Okay, so delta T equals the temperature at C minus the temperature at B. Where did we end up at point C here? Minus the temperature where we started at point B. To find the temperature at point B, we're simply going to use the ideal gas law where we solve for the temperature. And we are going to use our adiabatic relationship between pressure and volume to find the pressure at point B. We're given the pressure and volume at point A. We know A is connected to B via an adiabatic process. We know that an adiabatic process for an ideal gas obeys this law, so we can find the pressure at point B. Once we do that, we can just plug that into our ideal gas law and find the temperature at point B. Likewise, at point C, well, we know that the pressure is the same as at point A, so that's just our initial pressure where we started at. And we know that the volume at point C is half of our initial volume. So for these two, we simply can take the values that were given to us in the problem statement of the initial pressure and then half of the initial volume. And we get this value for our temperature. Notice that the temperature drops as the pressure decreases, right? So we were extracting a lot of heat from the gas because we were dropping the temperature and decreasing the pressure. Okay, now all we do is we plug into our delta U equation and we find that our delta U is negative 1841 kilojoules, which is equal to the heat transferred. So there is 1841 kilojoules of heat being removed from the gas in this process. Now let's look at the final step in our cycle where we move at constant pressure from point C to point A. In this case, both heat and work contribute to the change in energy of the gas. So we can first find the work using the negative integral of P dV. Because P is a constant, we can just pull it outside of that integral and we just get an integral over dV. Solving the integral, we get negative 450 kilojoules of work done on the gas. Because the gas is expanding, we expect negative work to be done on the gas. So the negative sign makes sense there. Now, the change in energy of the gas, we can also find, which is simply the using the equipartition theorem again, where we use the change in temperature. We just calculated Tc, and Ta can be calculated just from initial conditions using the ideal gas law. Plugging in those two temperatures, we get a value for the change in energy of the system of 1124 kilojoules. So energy is added to the system even though the work done on the system is negative. That means that a lot of heat must have been added to the system. How much heat? Well, it must be the difference between the change in energy and the work done, which is 1575 kilojoules of energy in heat had to be added to the system as it expanded. Logically, this makes sense because if you think about a gas expanding naturally, right, if I don't add heat to the gas, say I do it isothermal, adiabatically, right, there's no heat that enters the gas. In that case, the gas is doing work on its surroundings. That work means that it's losing energy as it goes, so it should be getting cooler, right, because energy is directly proportional to temperature through the equipartition theorem. So we would expect an expanding gas to get cooler, but in this case, it actually gets warmer. This Ta is warmer than Tc. How do I know that without actually having explicitly calculated it? Well, I know that temperature is directly proportional to pressure times volume through the ideal gas law, right? If I know that PV equals NKT, well, P times V at point A is larger than P times V at point C. V is larger, P didn't change. PV for A is larger, which means that there must be a larger temperature because I didn't change N, right? So just from looking at the graph, I can tell A is at a higher temperature than C. And normally when we expand a gas without heat flowing, we would expect that the gas would cool down. But instead, we've seen that the gas actually heats up. We're expanding the gas and it's heating up, which means we must be adding a lot of heat to the gas to keep the pressure constant as it expands. Okay, so we've added a lot of heat to the gas, even though the work done by the gas was, or the work done on the gas was negative. Now let's look at the total change in energy, total work done, and total heat added to the system as it moves through the entire cycle. So when we have total work, we just add up the work from each of our sections and we get 269 kilojoules. For heat, we add up the heat from each of our sections and we get 266 kilojoules. Now these two answers should be exactly the same, but because I did roundings in my calculations as I went through, we ended up with a slight difference here. So really, these two quantities, our total work, the total work done by the system should be exactly equal to the negative of the heat added to the system, because we need our total energy throughout the entire system to be 0. That is, we need Q to be negative W. So that doesn't quite work out because of rounding in our calculations. We end up with a slight difference here. But if you actually keep every single decimal throughout the entire calculation, those will come out to be the same. And physics tells us that they need to be the same. Okay, so just some slight rounding errors there. But we do find that the total change in the energy for the full cycle comes out to be 0. Now, this cycle here has a positive work done and a negative heat, okay? So heat is being taken out of the system and positive work is being done on the system, okay? So let's see why that is the case. Well, here, if we look at the work done, we have the positive work done as the system is being compressed. Compression leads to positive work, is this full area here. All of this area is the positive work that is being done in the compression of the system. While the expansion of the system follows this purple line here, which means that the negative work done on the system as it expands is just in this purple shaded region here. So we have a larger positive work being done in compressing the system because it is done at a higher pressure. Then we have expansion, negative expansion work being done because the expansion is done at a lower pressure. So that means that positive work is being done on the system. We compress at a high temperature, takes a lot of input work on the system to compress it. We expand at a low pressure, having the system do, it takes less negative work to expand the system at a low pressure. We can see that from the smaller area. So this system has positive work done on it and gives off heat. Q is the heat added to the system, that is negative. So this, but in general, the total change in energy of the system as a whole is 0.